In the fifth part of this video on the Java Collection Framework, we will discuss the various kinds of queues that it provides. In addition, we will also explain how a heap is used to implement a priority queue. We begin with a discussion of the two queue interfaces. The first of these two interfaces is the queue interface, which has two primary operations. The first of these two operations is the enqueue operation, which involves putting an element onto the queue. There are two methods that implement this operation, which are offer and add. The only difference between these two methods is how they handle the case when the queue is full. The offer method returns false in that case, whereas the add method throws the illegal state exception. The second of these operations is the dequeue operation that removes an element from the queue. It too has two methods that implement it, which are poll and remove. The only difference between these two methods is how they handle the case when the queue is empty. The poll method returns a null in that case, whereas the remove method throws the no such element exception. The second of these interfaces is dec, spelled the same as dequeue but pronounced dec. The prefix DE is an abbreviation for double-ended because this interface defines a double-ended queue. It has a total of 4 primary operations. There are two enqueue operations which are implemented by the methods add first and add last, which add an element to the front and back of the queue respectively. Like the first queue interface, it also has offer first and offer last methods. There are also two dequeue operations which are implemented by the methods remove first and remove last, which remove an element from the front and back of the queue respectively. This interface also has the corresponding poll first and poll last methods. Although queues can be used for a variety of purposes, one common use is by operating systems for scheduling. Next, we consider the classes that implement these interfaces. We begin with the two classes that implement the queue interface. The first kind of queue is the first in, first out queue, in which the first element enqueued is the first element dequeued. In that case, one would use the linked list class that we have already discussed. Because it is possible to efficiently remove an element from the front of a linked list is the ideal implementation of a first in, first out queue. The other type of queue is a priority queue. With a priority queue, the element dequeued each time is always the highest priority element on the queue. The class to use in that case is, not surprisingly, the priority queue class. It is implemented with a data structure known as a heap that we will describe shortly. Next, we consider the implementations of the dec interface. As we have already explained, this interface defines a double-ended queue. Both the linked list class and the array dec classes implement this interface. The linked list class is implemented with a doubly linked list, which is why it is a suitable implementation. The array dec class uses a resizable circular array. Because it is circular, no shifting is required on either end, so it too is a suitable implementation. Next, we consider how a priority queue can be implemented. There are a variety of possible implementations, so let's consider some of them and evaluate them according to the efficiency of the associated operations. One possibility is to use an unsorted list using an array. Because it is unsorted, the enqueue operation could be done in constant time, because the new element could be appended to the end of the list. The dequeue operation would require a linear search to find the highest priority element. The next possibility would be to use a sorted list. By keeping the highest priority element at the end of the list, the dequeue operation could be done in constant time. But the enqueue operation would require a search to find the location to insert the new element, and then the elements to the right would need to be shifted, making this operation linear. We can think of a heap as a partially sorted data structure. With a heap, both operations are equally efficient and, as we will see shortly, run in logarithmic time. Now let's consider the definition of a heap. First, it must be a complete binary tree, which is a binary tree in which every level, except possibly the last, is completely filled, meaning that all possible nodes are present. On the last level, all nodes that are present must be as far left as possible. In addition, the binary tree must have the heap order property, which means that the value in each node is greater than or equal to that in both children. Consequently, each branch of the tree is in sorted order. However, there is no particular order among nodes on the same level. That is the sense in which a heap is a partially sorted data structure. Next, we will examine the heap data structure in greater detail. On the left side of this slide is a complete binary tree. Notice that all nodes of a binary tree with 3 levels are present, except for the node that would be the right child of the node containing 3. The nodes are numbered in what is referred to as a level order enumeration. Although a heap is thought of as a binary tree, the data elements are actually stored in an array. Below the tree, we have shown the corresponding array. Because the tree is complete, the following formulas can be used. For any node in location n in the array, with the exception of the root, its parent is in location n over 2. With the exception of leaf nodes, its left child is in location 2n. And again, with the exception of the leaf nodes, its right child is in location 2n plus 1. To better help you understand the mechanics of a priority queue implemented with a heap, let's watch an animation of what occurs on both the NQ and DQ operations. Shown on the screen initially is a priority queue that already contains 6 elements. Notice that along each branch, the values in the nodes are in sorted order. But among siblings, there is no particular order. Notice also that the red bar at the bottom contains the array in which the elements are actually stored, which is a level order enumeration of the values in the tree. To begin, let's NQ one element, first choosing a small value. Notice where the new node was added, at the bottom level to the right of the previously rightmost node. Adding it there ensures that the tree remains complete. Because we chose a value smaller than what was in its parent, the tree still has the heap order property. Now let's add a large value, one that is larger than what is in the root. Because the tree was a full tree, the new node was added as the leftmost node on the next level to again ensure that the tree remained complete. This time, the tree is no longer a heap, so let's click the Step button. Notice that the value in that node was swapped with its parent because the value in its parent was smaller, but it's still not a heap, so let's click Step once more. But it's still not a heap, so let's click Step one final time. Now it is again a heap. What is important to notice is that this operation requires examining at most one branch of the tree. The number of nodes on any branch is logarithmically related to the number of nodes in the tree, which is why this operation is efficient. Next, let's perform a DQ. The root always contains the largest value, so it is DQ'd. To preserve the completeness of the tree, the value in the rightmost position on the lowest level was moved to the root. But now it's certainly no longer a heap, so let's click Step. Notice that a swap occurred, but with the dequeue operation, a decision must be made whether to swap with the left or right child. The larger of the two is always chosen to ensure that the heap order property is achieved. At this point, we need to click step one more time. At this point, it is now a heap. What is again important to note is that it was only necessary to examine nodes along one branch of the tree, which is why the dequeue operation is also logarithmic. Finally, let's consider a program that makes use of the Java priority queue. This program illustrates how a priority queue can be used to perform a sort by first enqueuing all the elements and then dequeuing them. Here is the declaration of an instantiation of the priority queue. In the first loop, integers are repeatedly read in from a file and then added to the queue until the file is empty. Then they are repeatedly dequeued and then displayed until the queue is empty. Next, let's run this program. Notice that the output is in sorted order. Notice also that a priority queue allows duplicates, so they have not been removed.